Hi everyone, thank you so much for joining us today. We have with us Arthur, who is a senior research scientist at Google DeepMind. He got his PhD in 2022 from Sorbonne University in Paris for his work on continual learning. He's working on making training more collaborative through distributed training. In this work, he will be presenting his latest research on distributed low communication training of language models. Thank you so much for joining us today, and over to you.
Thank you very much, and thanks, Ahmad, for the invitation. So today I'm going to present you our recent paper that we put on archive a few months ago, DiLoCo, for distributed low communication for training large language model. So first of all, it was a team effort that we did mostly early last year with this team. It's amazing co-workers. I'm going to start with the goals, that what we wanted to achieve and why there was a problem in the first place, and then how we solved that. So there is many flavors of parallelism. So parallelism is a way to distribute compute across devices. For example, you could have two GPU and you want to use not one training for one GPU, one training for another GPU, but you want to use one training that use both GPU. So you want to distribute compute. Distributed compute is very useful in current era, where the goal is basically to do maximize the scale, to do bigger model, more data. You need to distribute compute, otherwise you're gonna take forever on a single device, and it's not possible anymore. There is many flavor of parallelism. If I want to generalize, two big flavors would be the data parallelism and the tensor parallelism. Data parallelism is how can you distribute your compute to process more data at the same time. So for example, I have two devices, device A and device B, could be two different GPU, usually the same hardware type in order to get the same speed. I'm taking my batch of data, that is a huge batch, but then I divide my batch in two, first half and the second half, and I'm giving each of them to our model in order to process twice more data across two different devices. Then on the right, you have the tensor parallelism. There's also another alternative called the pipeline parallelism. The idea is similar. Basically, in tensor parallelism, is like if your model is too big, you cannot process it on a single device because there's too much parameters. Therefore, you can just split it across multiple devices. In our case, we're going to focus on data parallelism only. So our method is compatible with data parallelism, tensor parallelism, etc., but it's a new kind of data parallelism. So what is data parallelism? In practice, it allows you to compute more data given multiple devices. So we're going to have on the two devices, each of them will hold a replica of the model, the same parameters. Then we're going to do a forward with different subset of the data on each of them. We compute a per batch loss on each device. We compute the gradient on each device, and then we all reduce. So that's from the distributed computing nomenclature. We do all reduce of the gradient, meaning we communicate the gradient of each replica together, and we apply them, meaning that at every time step, our devices, each of them hold two replica of the models with the same parameters. The problem is that you need to communicate at every time step. Communication is fine usually, and that's what we do when we have like multiple GPU that are located in your same computer. The communication is very fast and much the time spent in communication is much lower than just the time spent to do forward and backward. So that's okay. But what if you want to actually to scale to non-collocated devices? For example, device A could be in the US, device B could be in the UK. Here, to do the synchronization, it could take maybe 1 second, while forward, backward would only take maybe a quarter of a second. Meaning that now we are wasting a lot of time during training to do the synchronization, which means that we cannot do data parallelism with non-collocated devices. So our vision, the vision of our team in general, and that's this paper is only one first step toward that vision. We want to be able to do worldwide collaborative training of large language model. So it's similar to some idea that, for example, have been explored by Hugging Face. We want to be able to train our model across the world with everyone collaborating and sharing the compute. An example, for example, is university could pool their resources, so they don't have as much resources as Google, Facebook, or NVIDIA. So they could simply pool their resources between all universities together in order to train a bigger model together. So that's similar to some also stuff that have been done, for example, with Bloom, with Hugging Face. And the idea is that, sure, everyone has maybe a few GPU there, a few GPU there across different countries. That's not a lot, but that's a lot of breadth of compute. And if you can pull together all the compute for training a single model, that's actually a lot of compute, and that's our goal. So now I'm going to explain the model and how can we actually do a new kind of data parallelism, but with non-collocated devices across the world. So an idea that is simple is like if communication is that costly when we communicate across the world, maybe we should communicate less. Communicating less means that we cannot synchronize the model at every time steps, and we need to do some kind of independent optimization, meaning that each replica on different devices in different countries must be able to do a little bit of independent optimization before synchronizing back. So in order to do that, we draw a lot of inspiration from the federated learning literature, however, with some kind of different setting, as we are more interested into a distributed setting, which is slightly different, and we push that to the extreme. So this independent training that I'm going to explain allows us to do infrequent optimization and first to do a cross-country distributed training. For example, here our model could be distributed across the US, France, Japan, the UK. We could train them for a certain amount of steps that we call here inner steps. So they will be optimized with the forward and backward, and we apply the optimizer, multiple steps before doing the communication, meaning that each replica parameters will drift away a little bit before we bring them back together for synchronization. Here the communication steps. Another advantage that could enable us is that if they can be optimized separately before doing a communication very infrequently, we can actually use different kind of hardware. If we do data parallelism in a classical way where we have to synchronize at every time steps, you need the same hardware type. Otherwise, if you use, for example, a V100 and H100, very different speed, at the same time, the fastest unit has to gonna wait at every time step the slowest unit. In the end, it's not very useful. But if they can be independently optimized, it's maybe more useful maybe to have like one pool of compute which has a lot of V100, very poor GPU, another pool of compute which has a few H100, powerful GPU, and overall their speed are similar. So that could allow us to use heterogeneous devices, which is also useful because there is many devices in your pool center, for example, at your university, your company, but they may not be the same device type. So if we can all use device type together, that's pretty great. So the recipe of our DiLoCo algorithm. So usually we start from an existing model that was pre-trained, but that's very optional, and we show in ablation that we can also work with the model from scratch. We have K-worker. So these K-worker are like, for example, different pool of compute. Each worker could have a single GPU or many GPU. That's optional, meaning that each worker could do internally data parallelism, for example. Each worker is distributed across the world. We also have our data set that we split into K as much as worker. The splitting of the data set could be IID or non-IID, meaning that we could simply randomly sample data on each of those coworkers, or each coworker could have different kind of domain. Both of methods work quite well in our setting. And finally, we're going to need two optimizers, what we call the inner optimizer and what we call the outer optimizer. For those familiar with federated learning literature, usually they use the term of client OPT and server OPT. Client optimizer, server optimizer. But that's interchangeable terms. Now, for every round of optimization, we have what we call outer steps. So we can do, for example, a few hundreds of outer steps in our case. For each outer steps, we're going to train each worker on their own data, their own replica, for a certain amount of steps, certain amount of inner steps. So as you can see here on this diagram, I don't know if you can see my screen. No, you cannot see my screen. So as you can see here, we start from the same parameters, and then we do a little bit of independent optimization until we train theta1 and theta2, each of them two different replica that may have drifted a little bit since they were not optimized together and they were not synchronized at every time steps. We synchronize it with we simply train them independently, and we use an inner optimizer, which in our case is Adam, but you could use any other optimizer that you want. We apply our setting on language modeling, so classical language model laws for decoder transformer, but that work well with probably any other architectures. Then we need to do the synchronization, and that's where it is interesting. After doing each inner steps, each of the model have been drifting away, and now each replica has different parameters. We need to synchronize them. So what we do, we compute the delta between each replica and the initial point. For example, the difference in the parameter space between θ1 in blue and θ0 in gray. Likewise, in θ2 in yellow and the original point in gray. So this delta in the parameter space, we call it an outer gradient. It's not a proper gradient. As you know, a gradient is defined as an infinitesimal difference. Here, that's not a very small difference. It's a difference across hundreds of steps, as we can do, for example, hundreds of inner steps, meaning that's a delta in a huge difference of time steps. But luckily for us, it can still behave more or less the same. As we can take this outer gradient, we take the average of all outer gradient, and we can apply an optimizer on it. If this outer optimizer is SGD with learning weight equal 1, it's simply equal to the model averaging that you may have seen in literature called souping, for example. In our case, closer to federated learning, if we were to do this multiple times, that's what we call federated averaging from a paper of federated learning in 2016 by McMahon. However, we found best performance by using another optimizer that no one used before, to the best of our knowledge, Nesterov. The simple and old school Nesterov is actually working very well in our setting. So simply, it's SGD with learning weight 1, momentum 0.9, for example, and using Nesterov. So it's very pluggable and play with JAX or PyTorch, and we simply apply it on the outer delta. We believe that Nesterov could be useful, as you know, Nesterov can make a gradient correction, and that may be useful in our setting when our gradient, an outer gradient, is defined across hundreds of steps, and you may want to correct it in order to avoid overshooting some minima. So that's the method. The method is fairly simple, and despite that, fairly powerful. So we compare it against three baselines with different amount of communication, compute on data, and time spent. For simplicity here, we assume that we have 8 devices. This device could be either collocated or not. The baseline is only with one device, so there is no communication as it's only one device. It uses one time the compute, one time the time data, and a certain amount of perplexity, which is a measure in language modeling. You want to reduce the perplexity in order to get better. Then we have another baseline with data parallelism. So data parallelism that you probably have used. We need to communicate regularly. So we have 8 devices and we do n steps of training, meaning we need to do 8 times n communication cost. The time cost, luckily, is only 1 because we parallelize data parallelism. However, we need here like 8 times the compute, 8 times the data. But that reaches into better performance, which is good. Then we have another baseline where we use 8 times batch size with micro-batching. So in our case, micro-batching, we can use a single device. Simply, we will do multiple steps of forward, accumulating the gradient without applying the gradient. And once we did 8 times a backward pass, we can average all those gradients and apply it. So there is no communication because there's only one device. However, it takes 8 times slower because there is no parallelization, which is kind of harmful. And it uses 8 times the compute and data. And of course, it reaches the same performance as the previous baseline. However, because it has less device, it doesn't parallelize and it's slower. Then the last baseline, we use 8 times update. So with a single device, we are 8 times slower because we update and apply the gradient 8 times. We also use 8 times data. We reach better performance, but at the cost to be 8 times slower, which is also not very favorable for us. And then come our DiLoCo. So our DiLoCo, we also need to synchronize, but contrary to the second baseline, where we synchronize at every steps, and we do n steps in total, we only need to synchronize every time we do h inner steps. Meaning here, our communication cost is 8 times n, the number of steps, divided by h, the number of inner steps. Here, for example, in practice, most of our experiments are with h equal to 500, meaning that we communicate 500 times less. Because we are doing parallelization across L device, our time is only 1, our compute is 8, and we reach a performance that is as good as all the other baseline, except the before baseline, that was simply doing 8 times updates, but we are 8 times faster. So I would say this is an okay trade-off. We try different kind of optimizer. In the literature of federated learning, if we were to use as outer optimizer SGD, that will be fed average, one of the first big federated learning paper from McMahon. If we use Adam, it's actually FedOPT from the Reddy et al. Paper. However, we found both of those papers were not performing as well as Nesterov, to our surprise. We found that Nesterov was better in performance, much more stable across hyperparameters. We actually tried different hyperparameters, for example, for the outer learning rate, the outer momentum, and etc. And we found that Nesterov was very robust and having the optimal one for almost every setting, which is actually very good for us as we don't need to do extensive parameter tuning. And more important than that, we found that Nesterov was the only outer optimizer that allowed us to scale to hundreds of times in terms of inner steps, inner communication, meaning that we don't need to communicate every 10 steps, for example, as the classical federated learning literature do, but we can communicate every 500 steps, which is much less and then very useful in case you want to distribute compute across the world. Speaking about this resiliency to communication frequency, we did some experiments where we do different kind of communication. So for example, we communicate every 50 steps, 100, 500 steps, or even 2000 steps. You can find that if we communicate like very infrequently, up to, for example, 1000 or 2000 steps, performance start to degrade, but not that much. And if we communicate every 500 steps or 50 steps, we get roughly the same performance result while being much more communication efficient. One experiment that was also quite cool is that in practice, if you do, for example, as the example I said in the beginning, multiple universities or multiple individuals that pull all their resources together to train together a big model, sometimes some people will turn off their computer and you won't access to that computer anymore. Meaning that across the training, your amount of replica, your number of DiLoCo replica could change across time. So how well your performance will be, because meaning if you have less DiLoCo replica at one given steps, meaning you have less data, meaning that could affect the performance of your model. So we explore different kind of settings. So you can find here on the x-axis the training steps, on the y-axis the number of replica, how much basically devices we could have in parallel, and that could change across time. So you can find on some of them we try where we increase the compute, we decrease the compute, and etc. Different settings. So we have, for example, the constant distributed, where we use always 8 replica. The doubling compute, where at some point we double the compute, or halving compute, where sometimes we halve the compute, and likewise also the ramping up and ramping down, where we respectively ramp up the compute and ramp down the compute. So how well our behavior will be. And we found actually that, of course, if you have always the same amount of compute, that's better. But we found that all variation basically are not that much on how the compute is distributed across time, but whether how much compute you have in total. So for example, if you see here, you find that doubling compute and halving compute have different kind of behavior across time, but in total, we have the same amount of compute and we have the same performance. Likewise, for ramp up and ramp down, we have the same performance, meaning that the convergence is sensitive to the total amount of compute, but not how it is spread over time, which is a fairly useful property if you cannot control the overall compute pool, which is usually the case in our setting. We can also further reduce the communication cost. So DiLoCo amortize the communication cost by communicating only every 500 steps. The problem is that even it's very infrequent, there's still a communication cost that could be problematic. For example, if your model are very big, your gradients are likewise going to be huge, and this communication cost could still spend maybe a few seconds, a few minutes, depending on your bandwidth. So we can experiment also how to compress our outer gradient by pruning its value. We just tried a fairly basic method to compression, and we found that by compressing the values up to 50%, we had barely any difference of performance, less than 1% degradation. Likewise, if we were to prune 75%, we are still at worst close to 2% worse, which is still respectable given the fact that we compress a lot our communication and thus our information. Yes, Irem?
When you say pruning here, does this correspond to gradient sparsification type of parameter reducing, or is it like freezing some of the parameters?
Good question. No, it's simply we take the parameters, the outer gradient, the delta, for each replica, and then we simply zero per some of the row of each gradient, and then we communicate, meaning we have less bytes to communicate.
Yeah, that makes sense. So did you do the gradient selection randomly, or like did you select the top gradients, or?
The top values. And that's a very basic thing. We can do better.
Mm-hmm. Okay, yeah, thanks.
We also wanted to try a different model size. The model merging literature, so everything that is related to soup, for example, indicates that larger models are easier to merge. So we wanted to figure out if it's still true in our setting, where in our setting we do some model merging, but regularly across training and not just at the end of the training as the classical model merging literature. We did only preliminary experiments from 60 million parameters, 150 million parameters, and 400 million parameters. And we found that the scale could still be helpful to our setting. Those are preliminary experiments, and we wish to expand it to larger scale to figure out if that's a behavior that can also be scaled up to the billion scale model. So now I have shown you about DiLoCo, and that's great. I can tell you that we can communicate every 500 steps instead of communicating every steps. I can tell you that when you have to communicate, which is very infrequently, we can compress that communication to be even more bytes efficient on the bandwidth. But there's a problem. If you figure out in the beginning, I told you that in our setting, we could use different accelerator, for example, H100 versus V100, different kind of devices with different kind of speed on each, thank you, Aaron, on each replica. The problem is that we have some lagger, meaning that, for example, in that setting, I'm trying with a different kind of TPU and GPU. For example, the TPU V5 is going to be much faster than a GPU V100. That means that when we communicate, for example, if it's twice faster, when we communicate, the TPU V5 will have to wait for the V100 replica to finish its compute and in order to do the communication, meaning that the fastest replica have to wait for the slowest. And that's kind of defeat the purpose of our setting where we wanted to use different kind of replica. We need to do something else. We need to go away from synchronous communication, even though it's infrequent, and we need to go to the asynchronous communication. So this work is another paper that we published in January. The lead author was Bolio, who was doing his internship. He's finishing his PhD this year and he's a fantastic researcher. So if you want to work with him, please reach out to him. So I said that we wanted to do asynchronous. So what is asynchronous in that setting? We symbolize here, meaning that you have, for example, a fast device in blue and a slow device in pink. A synchronous setting, meaning that the fast device, even if it's finished before the slow device, has to wait for the slow device to finish in order to do the synchronization and start training the other outer steps. In the asynchronous setting, you can simply communicate, synchronize with the central server, which is simply a CPU unit, and you don't have to wait for the slowest unit. So each of your devices, slow and fast, will communicate and synchronize with the central server without having to wait for each other, meaning they will be synchronized at different moments in time, which allows us to simply do much more synchronization steps in total, given the same amount of time. So this is fairly simple to implement. So we implemented it, and we wanted to see how well DiLoCo will behave in an asynchronous setting. So does that work out of the box? Not really. So here I'm showing you two plots. In black, we have the synchronous DiLoCo, meaning we have to wait for every replica in order to synchronize. And then in blue, we have the asynchronous DiLoCo, where we don't wait and we synchronize with the central server, whether or not the other units already synchronize, and we continue our training without having to wait for the slowest replica. You can find on the right, we compare the perplexity, PPL, versus time. Of course, async is going to converge much faster than the synchronous because we don't have to wait in terms of time. But if we look on the left, in terms of total number of updates, we found actually that being asynchronous is actually harmful and our perplexity is higher than a synchronous setting. So that's a problem. We wanted to understand why. So we're going to take a very simple setting for our synchronous. we can take 4 devices, 4 replica, each of them with the same speed. For example, here device A, B, and C, and D have the same speed of 1.70 seconds per step. They have the same speed, and in our synchronous setting, they will synchronize each of them on the central server without having to wait for each other. So there won't be any stallness except that they are synchronized and then they go back to the replica. So that's the simplest setting where there is no stallness, no waiting for the other replica. And still, we find in our setting that our asynchronous DiLoCo is working worse than our DiLoCo. Meaning that even the slightest stallness in our outer gradient, here simply a stallness of simply 1 step, is actually harmful. So you can find on the paper, our lead author, Bolio, made a lot of experiments to understand where this behavior comes from. And we actually found that the culprit is in the outer optimizer. So remember, previously I showed you that the outer optimizer is an optimizer, SGD, Nesterov, Adam, whatever, that is applied on the outer gradient. I've shown you that we could do a basic setting, for example, an outer optimizer that would be SGD without any momentum. And surprisingly, this works quite well in the asynchronous setting. But if we were to use Nesterov, which has a momentum in our asynchronous setting, despite being very powerful in a synchronous setting, it didn't work for this asynchronous. Meaning that the culprit from the moment comes from the momentum of the outer optimizer. And we found across many experiments that both in our federated learning setting and also in more classical setting, that the stallness of the gradient or outer gradient is actually very dangerous for all the optimizers that have a momentum. We tried many settings from the literature and we found that the best solution was actually quite simple. Our solution is to update the outer momentum only once in a while. Meaning that, for example, every for every outer steps, every time that there is a replica that is communicating with the central server, we apply an outer optimization with Nesterov, with the momentum, but we don't update the momentum of our outer Nesterov. And then, once in a while, for example, every 10, we use all the outer gradient that we kept in memory in a buffer to compute a more precise estimate of the new momentum of our outer Nesterov, and we update it and we apply it. Meaning that simply, we can use our Nesterov optimizer at every outer steps, but we don't update the parameter of our Nesterov always. And that's actually the simple solution combined with a few other tricks, but that's the main part, allow us to get good performance. What are those performance? So let's see, for example, different kind of level of stallness. So you can find here on the left, we have the most basic, so no stallness, all the devices have the same speed. We have 4 devices and they have the same speed. So there is no stallness, that's perfect setting. We can find that DiLoCo and async DiLoCo in green and in orange are actually as good, which is expected because there is no stallness, there is no asynchronous setting. But as we increase the stallness, meaning for example, 2 devices A and B can be at the same speed and then device C and D can be slower. And we found that DiLoCo start to get worse, while async DiLoCo start to get better. And if we go to a very harmful setting, for example, where the device A go to 1.7 seconds per steps, and then the slowest one is maybe dozen or hundred of times slower than the fastest devices, you can find that here, the DiLoCo in blue is not working as well as async DiLoCo, and our async hours, that's another version, in green. Meaning that we manage with our simple solution to get an asynchronous setting that is working well, both with respect to time and with respect to the number of steps. This allows you to actually train with multiple devices across the world and devices of different kind, H100, V100, for example. Our setting, we are one of the few to actually try this kind of federated learning across the world for real, not an toy setting. So we actually train some models that are fairly big, a few hundred of millions of parameters, literally in Japan, in Norway, in the US, at different locations. That required a lot of engineering work, and thanks to all my coworkers. However, it was quite easy to do it because of all the Google infra. So we wanted also to give to the community a way to reproduce this kind of setting without having to have devices across the world for real. So we created some kind of data sets which is a multiple mixture of Gaussian, basically. These small data sets that can work in a collab. We tune it in a particular way, and we found that this toy setting that can be run on a collab with a single GPU or even on CPU, but that's going to be a bit slow. We found that it can now produce the same kind of behavior for both synchronous and asynchronous as our large-scale setting. So we hope that this collab that is available for everyone could be helpful to kind of reproduce our results and also maybe to improve them. So as a summary for this talk, we propose a communication-efficient distributed training algorithm. We take inspiration from the federated learning literature, but we synchronize much less. We synchronize every 500 times. That's 500 less communication, which is actually helpful to train a model for real across the world. We do experiments on language models up to 400 M. Our actual experiments are done across the world, but we also propose a toy setting. And we propose an asynchronous extension that can handle heterogeneous devices, which is very helpful for us as we can actually pull every kind of hardware we can find in Google and all use them in parallel. We have the tooling for the archive of DiLoCo and the archive of async DiLoCo. You can find on the second link of async DiLoCo a link to our GitHub where we provide the collab for you to reproduce our results. Do you have any question? Yes, Ricardo?
Hi, can you hear me?
Yes, I can hear you.
Yeah. First, thanks for your talk. It's been really very interesting to hear. I have a question about of your method about DiLoCo in the synchronous setting. I would like to understand if I understood correctly about the relation with other distributed learning methods. And essentially, DiLoCo is like similar to slow-mo, maybe. But the difference is mainly on the outer loop for the outer opt. Is it correct?
Yes, slow-mo is not the closest one, if I recall, as they also, if I recall well, they use some kind of SGD in the outer loop that bases statistics on also the inner loop. Our setting would be more, if you want to make a comparison, is like the FedOPT, for example. If you see in FedOPT, they use kind of our setting with inner optimizer, which is SGD, and outer optimizer is Adam. In our setting, inner optimizer is Adam, and outer optimizer is Nesterov. So you can find our setting as just an alternative where we switch some optimizer, yes.
Okay, thanks. And so you found that actually the difference between using Nesterov and classical momentum on the outer loop is significant, right?
Yes, absolutely. It's significant across different settings and it's much more stable. As you can find here, maybe I was a bit quick on that slide. You can find in blue Nesterov, which reached a performance of 15, while SGD in orange, a performance of close to 17. And for the SGD, with the outer SGD, we actually tune the outer learning rate. So it's not one, it's I think something like 0.8, the best one. And still, it was not as good as Nesterov by large margin. And other outer optimizer like Adam, for example, are very unstable. So for example, for the outer Adam, we had to play with the epsilon on the denominator of Adam in order to make it more stable. We need to increase it a lot. And that was very complicated.
Okay, thanks.
Okay. Yes, Johannes?
Hey, Arthur. Yeah, thanks for the talk. Really great. My question would be also to the synchronous setting of DiLoCo, to the algo there. It seems like the outer gradient you have there is just the rate reference, right, between the beginning and end of like one of the 500 steps then, right? And not like a...
What did you say?
Sorry, the outer gradient seems to be just the rate difference there, basically, right? And not like a true gradient, right? And
yes.
My question would be, did you try to like, average the gradients then? Or did this perform worse or, yeah?
No, we didn't try. If you mean that we average all the inner gradient together, we didn't try that.
Okay.
It may work well. We don't try that, but it will be very different, I think, as a behavior. We found actually some experiments where, in that case, if you average, it's not exactly the same because in our setting, we get some properties by applying the inner gradient at multiple times thanks to our inner optimizer, which is Adam and not SGD. So in that case, if your inner optimizer would be SGD, that would be similar. In that case, that's very different. But that's
Okay.
worthwhile trying, yes.
Interesting. Thank you.
I have a question from Rabius. If I wanted to apply DiLoCo in a local setting in FTP devices, what steps should I take? If I want to make a website like torrent reward base, is it possible? Yes, I think it will be possible. I think there's already a company in SF that try to do some distributed computing with some kind of crypto coin and stuff like this. So that will make sense probably to do that, especially since our model is resilient to the amount of compute availability. You could actually, Rabius, make some kind of a torrent system base where each of them could join into the pool and then work like this together. I think also Together AI is doing something similar. I need to check. Amen. For the data shards, if compute is heterogeneous, have you tried to send less data to compute nodes that have less resource? Okay, so Eman, let me rephrase if I understand correctly. If your compute is heterogeneous in the sense that you have different CAN, would it make sense to actually process less steps, basically, with the slowest unit? If that's correct, yes, we also use that. That didn't give as much gain as our delayed momentum update method, but we also use a method where basically we do less inner steps if the unit is slow. So for example, the TPU V5, which is the fastest device here in this list, could be trained and synchronized with the central server every 100 steps, while for example, the V100, the slowest here, could be doing only 25 inner steps and synchronize every 25 inner steps. And because, for example, the TPU could be, let's say, an arbitrary number 4 times faster than the V100, they could be synchronized roughly at the same speed because the slowest do less steps. Does that answer your question, Eamon? Yes, Rabius, you can. If you want to contact me to any question, please send me an email at Douillard, my family name. You can find on archive at google.com, and I will answer your question.
If you don't have any other question, I think we can end the session here.
Yes, thank you very much, Ahmad, for inviting me to this talk. I have a pleasure to talk about it with different people. I hope that this could help the community to train big model without have to collocate your compute, which is not very possible. I hope that the collab can be helpful. If you have any question, please send me an email and I'll be happy to answer anything you would like.
Thank you very much for the session. Really enjoyed it.
Thank you, Ahmad. Thank you.